All right, welcome back. So we're gonna start from a practice derivation problem today, just to demonstrate in how to approach these kind of derivation problems whenever you see it. And then we'll be moving on into application of the first law of thermodynamics. So hopefully today is more of a practice of application kind of lecture. So picking up from where we left over last lecture, we went over the definition of the Joule-Thomson experiment, refreshed our memory in heat capacity. So now let's think about what can we get by only using the definition of these terms in terms of derivation. Right, so this is one of the questions that it looks horrible if we think about it. First question asks you to derive equation 2.65, which is like the partial differential of enthalpy over pressure at constant T equals to negative Cp mu Jt. So why it is the case. Second one is trying to prove our mu Jt equals to this complicated long equation. And let's see how do we use our knowledge to approach these kind of derivation problems, right? So I listed several things that we discussed, basically definition of coefficient and terms, right? So we have the definition of mu Jt and mu J, or the Joule-Thomson coefficient and the Joule coefficient. We have definition of your heat capacity, isobaric heat capacity, Cp, and isochoric heat capacity. And then we have definition of enthalpy, H equals to U plus PV, and our isothermal compressibility. So these are all the definitions that we went over. So we'll be using everything here alongside with some calculus to prove that that equation is true. All right, so let's get started. If you already tried it, let's just go over it together. Maybe you'll have a different approach comparing to mine. All of them are correct if we can get the same answer. So starting from the first one. Now, when we're looking at this kind of derivation problems, where you're trying to demonstrate like the partial differential equation equals to sum of the coefficient that we defined, we always start by writing out what are these coefficients based on their definition. So in here, what we can write, well, on the left-hand side, this stays the same, dH over dP at constant T. And we can write out definition of Cp, right? So that's the isobaric heat capacity, or dH over dT at constant P, right? How does your enthalpy change with respect to temperature at constant pressure? Times mu Jt. So mu Jt, that's our Joule-Thomson experiment. We have the definition there, how temperature change with respect to pressure at constant enthalpy. And after writing it out, you'll soon find out, okay, so in here we have three variables interconnected with each other. So whenever you see this happen, it's a good hint for us to use our cyclic chain rule. So the equation we're using is basically dz over dx at constant y, dx over dy at constant z, and dy over dv at constant x equals to negative 1. So in here, if we're replacing x, y, and z with h, p, and t, what we're getting is, well, dh over dp at constant t times dp over dt at constant h, dt over dh at constant p equals to negative 1. Right. And effectively what we're doing is moving these terms to the right. And well, we have dh over dp at constant t, moving these things to the right, flip the top and bottom. We get dp over dp at constant h times dh over dp at constant p with a negative sign in between, and we get what we want. Right, so this one is our mu Jt, this one is our Cp. Very straightforward. Like what we're doing is simply writing down the definition of each of the terms we use in here, And then observe the pattern. Now we observe there are three variables in these partial differential equations connected to each other. So we're using the cyclic chain rule, and it's very straightforward to do the derivation here. So far, so good? Okay, and then we're moving to the more challenging one. So I'm gonna erase everything here because we already did the derivation, so we can use our equation 2.65. The next one is slightly more horrible to look at because you're trying to prove that mu jt equals to this long equation, right? But one of the things we know is if we move that CP term and the negative term to the left-hand side, well, we have our negative CP mu jt. So we're ready to use what we derived in the first part to use in my second derivation. So after moving the term, which is moving the CP to the left, basically times CP on both ends and negative on both ends, what we end up getting is negative CP mu jt equals to volume times chi CV mu j minus chi p plus 1. Or I can write this one out as like your dH over dP at constant t equals to, well, V chi CV mu j minus chi Vp plus V. All right. And then what do we have? You read the question, it gives you a hint of saying, okay, why don't you start by taking the partial differential equation of enthalpy over pressure at constant T? So that is saying we can use our definition of enthalpy in this derivation. So what we're using is H equals to U plus PV, and taking differential of H, we get dH over dP at constant T equals to du over dP at constant T plus pressure times dV over dP at constant T plus volume times dP over dP at constant T. So in here we're using several calculus rules, right? Some of them is like dx plus y equals to dx plus dy, or dxy equals to x dy plus y dx. So basic calculus, that's how we get to this expression. So far so good? Some of the terms in here, like this dP over dP, this one goes to 0. And now we have three terms, right? So we have the du over dP at constant t, p times dv over dP at constant t, and a simple volume. And on the top, we're trying to prove these two expressions are equivalent to each other. So by using basic calculus, we write out my dH over dP, and now we have three terms. We're trying to prove they're equal to each other. Some of them is pretty obvious. Like this volume term is already set, so I call this one like checked. My volume equals to volume. My dP over dP cancel out. And then we have two more terms we're trying to prove here. All right. So now we break down this problem into two parts. First part, we're trying to say my kappa times V times P equals to my dV over dP at constant T times P. That's this part. This is a negative, so I'm trying to have negative here. Yes?
Why did we cross that out again?
This one is dP over dP, that's how pressure changed with respect to pressure.
Mm-hmm.
So it's just one.
Okay.
It's not changing, it's like canceled out. Now for this one, what do we know? Let's look at the definition of kappa. Right, so my kappa equals to, by definition, that's my isothermal compressibility, 1 over V times dV over dP at constant T. It's just by definition true. Or the other way to put it is we know that by definition dV over dP at constant T equals to negative kappa times V. All right, so this one is also set. We're happy. And that's our negative V over dV over dP at constant T. Yes?
So you just to clarify, you're rearranging the definition of the isothermal compressibility to match the...
It's not to rearrange, it's just like looking at the definition of the isothermal compressibility. It's within the definition, the partial differential of volume over pressure constant T equals to the negative V times kappa. That's how kappa is being defined. So far, so good? So now we have our second term also set. All right. So we have one more thing left. And the last thing we're trying to prove is this V times kappa times CV times mu J equals to partial differential of internal energy times pressure, over pressure at constant T. So why don't we write out the definition of every term on the left-hand side? That's always how we started. So V times my definition of kappa, which is negative 1 over V dV over dP at constant T. And then CV, that's my du over dt at constant V. And mu J, or my Joule coefficient, that's my dt over dV at constant U. All right, so V, kappa, CV, and mu J. So on the left-hand side, we're rewriting that expression out using their definition. Some of the things we know, like this one, the 1 over V times V, this just, the first two terms just becomes what we want. Right, so this one is kappa, this one is V. And these cancel out, we get negative dV over dP at constant T. The volume and volume cancel out, that's what I mean. All right. And for the right-hand side, this is another hint. This one is, again, we have two partial differential equations of three different variables product to each other. So whenever we see this, we have a way to simplify the product of these two partial differential equations using the cyclic chain rule. So we're using that again. Writing it out, what do we have? We have du over dt at constant V times dt over dV at constant U, and then dV over du at constant T equals to negative 1. Or if I'm moving this term to the right, we end up getting du over dt at constant V times dt over dV at constant U, and we get du over dV at constant T with a negative sign in between. Yes?
That third term, the dV over du at constant T, where did that just appear from?
Oh, this is a cyclic chain rule. So remember, it's like we have like x, y, and z. So dx, dy at constant z times dy, dz at constant x, and dz, dx at constant y equals to negative 1. All right, so in here, we're just writing out the cyclic chain rule. These two are just equivalent to each other. I'm just replacing x, y, and z with u, v, and t. That's all. Yes?
So we're adding that in so that we can rearrange the right side of the equation.
Right, so we're getting there, right? So in this case, by writing it out, we now have one single partial differential equation instead of the product of two. So we're simplifying the original expression here. So getting back to what we have two terms product to each other, right? So this left-hand side, v times chi equals negative du over, dv over dp at constant t. And on the right-hand side, we have our du over dv at constant t. So writing it out, we have our v times chi times cv times mu j equals to negative of dv over dp at constant t times my du, well, there's also a negative sign, du over dv at constant t. Right, so my negative sign and negative sign cancel out. And then in this case, both of these partial differential equations are at constant temperature. So we can cancel my volume and that volume out, and we get my du over dp at constant t. And what are we looking for? We're looking for this entire expression to be equal to my du over dp at constant t. And thus we solve the problem. Yes?
So like during exams, will you be expected to do derivations this complicated, or will they be simpler, for the lack of a better term?
I actually don't think this one is very complicated. If you think about it, what do we use? Okay, guys, what do we use? We only use a cyclic chain rule, all right? And then we use the definition of terms. That's all. We're just using like a little bit of calculus and then moving things around. Like if you really think about like plug in the definition of all the coefficients, this is something that's straightforward to do. So for the exam, like this kind of question is like fair game. I will also give you a similar like hint so that you know where to start. I don't want to frighten anyone, but we have worse things to come. Okay.
Can you explain the conceptual difference between mu jt and mu j?
Well, so mu jt and mu j are two different kind of experiments, right? So if you look at the definition of mu jt, that is linking temperature and pressure with enthalpy. Now, mu j is another experiment scientists can set up that links relationship between temperature, volume, and internal energy. So again, in both cases, we're trying to build a link between either enthalpy or internal energy with something we can measure. So these are two different experiments. Yeah. Yes.
I kind of got lost after you did the chain rule
Sure.
for the second part right there.
This
down
one?
there. After you got the step below right there.
Okay.
What did you do after that? You just
After this, I just plugged in. On the left-hand side, we know that Vk, V kappa,
What's that?
equals to this negative dV over dP at constant T. On the right-hand side, we have these two partial differential equations, or the Cv mu j comes up to be my du over dV at constant T. Now, because these two partial differentials are both at constant temperature, so my dV and dV can cancel out.
So the negatives go away.
Yes, negative go away, dV you cancel, yes. I can't hear you, sorry, you might have to shout. dV over dP at on the left-hand side, this one? This one? This one? Okay, so it's change of pressure over change of pressure. And the change of pressure and change of pressure will cancel out to be 1. And that's you end up with only 1 volume. Yes?
So just to reiterate like what we were doing in total, so we have that equation from B, the negative CP mu jt dash, and then we decided to do dH, we can redefine it as dH over dP with constant T to equal that on the right side, and then we use the H equals U plus dV, and now we pretty much just set those equal to each other.
Right, so the question asks you to prove, right? So can you show that mu jt equals to negative V over Cp and times that long chain like kappa Cv mu j minus kappa P and plus 1. So it's like a long expression, right? So this is a demonstration of like looking at this kind of derivation problems. At the end of the day, we're just plugging definitions and use calculus to move terms around to demonstrate like these relationships are true. This relationship is there to make a connection between your mu j and mu jt, which are two different experiments connected to each other.
And why did we decide to do dH over dT with constant T? Could we have done it another way if we wanted to?
This one? This one is in the hint. That's like the question asks you to do that. Yes. Yes. I'll take one more question, and then we have to move on. Yes.
So kind of related to that, is it because you're doing the Joule-Thomson coefficient, that's why it's with respect to pressure?
Well, so in this question, it's without the hint, you'll have to think about a way in order to break down the left-hand side, which is your dH over dP at constant T, into something that's related to internal energy. So without the hint, the way you have to think about it is how do I link my enthalpy with internal energy? So that's the definition of enthalpy. And that's how you know to use that equation.
Okay, and then so if like it was the first equation was like negative Cp times the Joule's coefficient and not the Joule-Thomson, like if it was just the Joule's coefficient.
That's a different equation then. That's going to be the du over dv at constant t equals to negative cv times mu j. That one we also did a derivation last lecture.
So if we do that, would it be like that starting equation, would we be doing everything with respect to the bottom?
Okay, don't think about things that doesn't happen, all right? It's a different question. It's a good practice if you want to try it yourself and see what you get. Okay, so this is a quick demonstration in what kind of derivation problems I expect you to know. And by the way, I'll post my previous exams before the actual exam, so you'll have an idea about what to expect later on. So now let's move on to next lecture. I'm already one lecture behind, but I think I'm fine. Okay, so starting from this lecture, remember in our previous lectures, we went over definitions of first law of thermodynamics. We went over definition of work and heat, which are two process-dependent function in thermodynamics, right? So work and heat are only defined for a specific process, right? There must be a transformation so that we define process and work and heat. And then we went over definition of some of the state functions. So those are my enthalpy, my internal energy. So now we're ready to use our first law of thermodynamics, and we'll start from simple terms, which is ideal gases or perfect gases, and trying to see how do we apply the first law of thermodynamics to actually get like numeric answer or expression of my ideal gas transformations. All right, let's get started. So first law and perfect gas. So if you think about my first law and perfect gas, before we move on to, yes?
I'm so sorry, is perfect gas the same as?
It's the same as ideal gas in this class. Your textbook used different nomenclature, so I follow up, but they're effectively the same thing. So when we're talking about ideal gases or perfect gases, remember what do we have? We have PV equals nRT, and in addition, we also have one more term that's true for ideal gases only. That is your internal energy is independent from volume. Or your internal energy for ideal gases is only a function of temperature for ideal gases. And this is one of the logic you have to feel about it. Like when we're saying ideal gases, we're saying like the gas particles do not interact with each other. There's no intermolecular forces whatsoever. So that means it doesn't matter how far away your gas molecules are, right? So they can be really close to each other, they can be really far away from each other, but as long as we're treating them as ideal gases, they don't talk to each other. So no intermolecular forces, and thus it doesn't matter how close or how far away your gas molecules are, and hence your internal energy doesn't depend on volume. It only depends on temperature, or how fast your gas molecules are moving, or kinetic energy in general. With that in hand, we can simplify some of the terms that we discussed, like heat capacities. So if we think about heat capacities, the original definition of heat capacity is CV, the isochoric heat capacity, equals to partial differential equation of internal energy over temperature at constant volume. But since we have your internal energy independent from volume, we can rewrite my CV to be equal to normal differential of du over dt for ideal gases. Or the other way to put it is you can have du equals to Cv dt for perfect gas. Question?
Yeah, just really quick. So if the problem doesn't specify ideal gas, then we just use our original definition.
Yes.
of CP
So
if it's-
if the problem doesn't specify ideal gas, you can use this one if it didn't say anything. If the problem specified ideal gas, then we have the second term to come true.
And it'll be like self-explanatory, like it'll explicitly say.
Yeah, we'll make sure you know what the question is talking about. If it is an ideal gas, well, make sure you'll see me saying for an ideal gas, blah, 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 like calculate delta H, calculate Q and W. Or for an ideal gas, undergo reversible PV work only. We'll make it very specific so you know what equation to use. If we did not specify, then it's a different story. Okay, and the same applies to enthalpy. Right? So we have internal energy not dependent on temperature. For enthalpy, if you think about ideal gases, what's the definition of enthalpy? We have H equals to U plus PV. And for ideal gases, like for example, if I ask you if enthalpy is dependent only on temperature, how do you prove it? Now for ideal gas, we have PV equals nRT. So your enthalpy will equals to U plus nRT. So naturally, your enthalpy is also only dependent on temperature for ideal gases. All right, so we can do the same kind of transformation of rewriting my dH equals to Cp dt for ideal gas. All right, now with these two new expressions, what else can we do? In our last lecture, we went over a derivation of, in general, what is the difference between your Cp and Cv, between your two heat capacities? So let's do that for ideal gas using two different ways. Now, thinking about Cp minus Cv, if we're using what we did today, we have like Cp equals to your dH over dt. Well, so that is dH over dt minus Cv equals to du over dt for ideal gases. And we know H equals to U plus PV, so we can write that as du over dt plus, well, d nRT over dt minus du over dt. And solving that equation, the du over dt cancel out. You're solving that equation to be nR. Right, so for, yes?
Sorry, where did the volume term go?
Oh, so the PV, okay, so H equals to U plus PV, right? So my PV equals to nRT. So this is my PV term. Yeah.
Why did you have to do that though? Why did you have to change it from?
Well, PV equals to nRT, and we're taking a differential over temperature. You want to make your life a little bit easier, right? All right, so this is a super quick derivation to say, okay, for ideal gases, we have the difference between your Cp and Cv equals to n times your gas constant R. So let's do it in our general way that we did last time. So to refresh your memory, in our last lecture, we went over the derivation of Cp minus Cv equals to du over dV at constant T, our internal pressure, plus pressure times dV over dt at constant P. So that's the derivation we did in our last lecture. This is generally true. And now, from here, what do we have? For ideal gases, we know that your internal energy is not dependent on volume. So this term becomes 0. There's no dependence of internal energy on volume at constant temperature. Or the other way to put it is your internal energy is not going to change when temperature is not changing. So this becomes 0. On the right-hand side, we have our dV over dt at constant P. Now for ideal gases, we have PV equals to nRT, or you can rewrite V as like nRT over P. So your dV over dt at constant P will give you nR over P. All right. And now this Cp minus Cv term becomes, well, 0 plus P times nR over P. My pressure and pressure cancel out. We end up getting nR. And we're happy. We can get the same answer using different methods. Yes?
So could you explain the first part of why you would be a constant P0?
Right, so for ideal gases, we went over ideal gases is only the internal energy and enthalpy of an ideal gas is only a function of temperature. And that's because we define ideal gases as no intermolecular forces, right? So that means when my temperature is not changing, when my temperature is kept constant, my internal energy is not going to change with respect to volume. So that's why this term becomes 0. Yes?
How did you get that dV over dt at constant P equals nR?
Oh, this one. Well, we're looking for how does volume change with respect to temperature, right? So we're looking at a volumetric equation of state. What is the equation of state for ideal gas? That's PV equals nRT. So I'm just rewriting my that's big. So I'm just rewriting my volume by moving my pressure to the right-hand side. So from PV equals nRT, you have V equals to nRT over P. And you take the differential equation of my dV over dt, that's just nR over P. We only have one temperature in there. So far, so good? So again, in this class, we will encounter this very often. There are different ways you can solve a problem. As long as it gives you the consistent answer, you know you're right. So that's one of the beauty of thermodynamics. So you can check your answer without talking to anyone or checking the textbook. Okay, and now let's move on to think about how else can we apply our first law of thermodynamics in systems of ideal gases, and look at an example question together. So this part is, again, application of the first law. Imagine we're talking about only with ideal gases, reversible PV work. All right, so in our first law of thermodynamics, we say that the internal energy of an isolated system is conserved, and we can write my du, or the infinitesimal change of internal energy, equals to dq plus dw. And since we know something about these terms for ideal gases, like for du term, we just went over the definition of heat capacity, right? So we have Cv dt equals to du. And also for reversible PV work, we have dw reversible equals to negative pdv. So at the end of the day, we can simplify my first law of thermodynamics for a system of ideal gases, reversible PV works, to be Cv dt equals to dq minus pdv. And we can start to use these relationships to solve for actual numeric answers in a specific, thermodynamic cycle, if you may. And let's look at one of the example 2.4 together. So in here, we read the question. We tell you there's like 0.1 mole of a perfect gas with Cv, the molar isochoric heat capacity, Cvm, equals to 1.5 R. We tell you this CVR is independent of temperature. So saying the heat capacity is a constant. And this perfect gas undergo a reversible cyclic process, go from 1 to 2 to 3 to 4, which is shown on the figure on the right. So in this case, we're looking at, isochoric process followed by isobaric, then isochoric, and then isobaric. We can easily replace each of these terms with maybe a tilted line or even a curve. But in this case, we're only looking at isobaric, isochoric as an example. And it's telling you, well, either P or V is held constant in each step, and can you calculate heat transfer, work, and delta U for each step and the entire cycle? All right, so for this kind of question, I highly recommend before you start, write down what do you know. Like write down the definition or the terms that we know that's specific to this system, right? So in this case, we read it. It's a perfect gas. So we know that PV equals to nRT. And we derive the relationship of your CP and CV, right? So we have CPM equals to CVM plus R. Remember, these are molar heat capacity. And that's just your heat capacity divided by N. So that's for perfect gas. Reading the question, we know it. We know the process is reversible, cyclic process. So for reversible process, PV work process, we can do the dW equals to negative PdV. And then for cyclic process, we have delta U equals to 0. So I'm gonna do one of the steps with you, and then you can try it yourself. And at the end of the day, you can do the calculation of adding everything together. It should all add up to be the same delta U for like the entire process. The entire delta U should add up to be 0. Right, yes?
How do you think of the relationship between CPM and CVM? Is that from the molar?
That's from here. That's the one we just did. Right, CP minus CV equals NR, and your molar heat capacity equals to CP minus divided by N. I mean, it's okay if it's not on the top of your head right now, but that's why I highly recommend you start writing out your own formula sheet so you know where to find this information. Okay, so I'm gonna clean out the board and tell me which step you want me to do. 1 to 2, 2 to 2 to 3, 3 to 4, 4 to 1. If nobody says anything, I'm just gonna do like 1 to 2. So for the process of 1 to 2, we can first write down what is happening in the process, right? The volume is changing between, well, the volume is not changing. It's constant volume process. So my volume is always equals to 1,000 centimeter cube. That tells us my volume is not changing. So we want to use my isochoric heat capacity. And this should be CVM. My pressure is changing from 1 atm to 3 atm. So several things you can instantaneously grasp. It's asking us for Q, W, and delta U. So in this process, since my volume is not changing, my work reversible, 1 to 2, equals to negative PdV integral. My volume is not changing, so my work must be 0. All right. And what about Q, the heat transfer? Now the Q equals to my CV dt from T1 to T2, CV dt. And we know what is CV, that's 1.50, and it's a constant, NR, and dt is just T2 minus T1. Right, and do we have numbers here? Well, N equals to 0.1 more, so 1.50 times 0.1 more, times your gas constant R. I'll keep R here because we'll cancel out later on. And your temperature equals to PV over NR. So PV2, well, P2V minus P1V over NR. My N actually also cancel out. Right, so temperature PV equals nRT. And, well, my NR cancel out with each other. My volume is a constant, so we end up getting 1.50 times, well, 3 atm minus 1 atm times 1,000 cubic centimeter. And you can get a numeric answer by doing this calculation. And it's the same for the rest of it. And my delta U obviously equals to W plus Q. And in this case, it just equals to my Q1. Yes?
Is it okay to leave the units for heat and atmosphere times centimeter cubed, or do you want to start change it?
It doesn't matter. I'm not going to dig that point because of unit is different unless I specified it. So for this question, it's okay to leave it as like centimeter cube times ATM. But if I specify to say like, hey, present your energy in joule, then you want to do the unit conversion. Yes. Oh, 1.5, this one? Well, this one is your CV, which is, okay, so here's, why do we know we want to use CV? It's because we observe the process being an isochoric process where your volume is not changing, right? So for a isochoric process, we're using our volume, the isochoric heat capacity, which is CV. And in this case, the CV value is given in the problem. So that's why we're just plugging the numbers. It's effectively just plugging numbers, but you want to get familiar with all these terms and definitions so you know what is the right number to plug in. And imagine now we're talking about process Q to 3. Now we have an isobaric process. So naturally, for this process, you calculate the QP, you must use the isobaric heat capacity. So it's more like observing the question and know what property to use. Yes?
Do you mind just doing an isobaric?
I don't, but we can do, let's do this one. Let's do the 4-to-1. Let's do this one. I'm just gonna do it on the board, right? So when we're looking at the isobaric process, so step 4-to-1, what do we have? It's isobaric, so my P4 equals to P1 equals to 1 ATM. My volume, V4, equals to 2,000 centimeter cube. My volume 1 equals to 1,000 centimeter cube. The same idea applies to our calculation. What else do we have? We have work reversible equals to the integral of negative P dV. So in this case, my pressure is constant, my volume is changing. That becomes negative 1, well, pressure times my V final over V initial. So V1 is my final, V4 is my initial. So V1 minus V4, and that ends up to be negative 1 ATM times 1,000 minus 2,000 centimeter cube. And you plug in numbers, translate, and eventually we get something like 101 joule. And what about the heat capacity one? So for the heat capacity, for my 4-to-1, again, for any processes, my heat capacity is defined as like CPR equals to dQPR equals over dt. So that's one of the definition of my heat capacity, if we still remember. Right? So heat capacity defines how does the heat transfer change with respect to temperature. So in here, we have 4-to-1. We have isobaric process. So we must be using the isobaric heat capacity. So that becomes my final over initial and times the Cp dt. All right, so what is my Cp? Now, so my Cp equals to Cv plus Nr, or Cvm plus R. So that gives me the 2.5 Nr, and times your final minus initial. So T final, which is my T1, minus T4, and my temperature equals to, PV equals to nRT, so temperature equals to PV over nR, right? And you can plug in the number, you get 2.5 nR times P1V1 NR minus P4V4 over NR, and my NR and NR cancel out. We get 2.5 times, well, pressure is the same, 1 ATM, and my V1 minus V4. And again, you can plug in the numbers into the calculator. You'll get something of negative 253 joule. Yes?
I'm trying to connect this to the first one. So for 1 to 2,
Mm-hmm.
if you want to like rewrite it, it would be CV and delta P.
Okay, so for the difference between this one and this one is a isochoric process, so the volume is constant. That's why we're using CV for the process, right? So when we're using the heat capacity to calculate the heat transfer, now for any process, so some kind of process, the C process equals to dQ process over dt, right? So if this process is isochoric, then we have CV equals to dQV over dt, which is the one we use for the first case. Or we have Cp equals to dQp over dt. So that's the one we're using for this one, because it's constant pressure process. All right. And then, well, what is delta U? Well, using the first law of thermodynamics, now delta U equals to W reversible 4 to 1 plus Q 4 to 1. And you just add these two numbers together to be negative 1, 5, 2. How are we doing so far? I mean, this is also a different kind of problem that you could expect in your exam and homework, which is applying what we learned in a actual specific setup to get numeric answer from it. And then we have about 4 minutes left, so I'll raise a question instead of giving you answer, and in our next lecture, we'll do that together. So now think about a process that is isothermal expansion. So when we have isothermal expansion, you might want to think about what is the heat flow for this isothermal process? What is Q for this isothermal process? Note that we cannot use this equation because no heat capacity is defined for isothermal process. But no heat capacity is being defined doesn't mean your heat transfer is 0. All right, so I'm going to leave here as a question, can you write out an expression of heat flow for an isothermal process involving ideal gas and reversible PV work only? All right, several things we know, right? We have delta U for ideal gas is only a function of T, or internal energy is only a function of T for ideal gases. So what do we know? We know delta U equals to 0 for isothermal process. What else do we know? We have our first law of thermodynamics, which give us my delta U equals to Q plus W. So the matter of this question becomes, when my delta U equals to 0 for this isothermal expansion or contraction of ideal gases, how does my heat and work change? So this is a very common misunderstanding because it's really easy to think about heat just relates to temperature. But this is a good demonstration to try it out and see like, okay, how do you solve an expression of heat flow for this isothermal expression of ideal gases? Reversible PV work only. And we'll go over this next lecture. We'll also go over adiabatic processes. We'll have a summary on how to calculate thermodynamic properties with ideal gases. And that next lecture will be the end of chapter 2. All right?
It's just a negative work reversible.
Yes, but it's a little